And I guess I should turn all this good stuff on. So today's topic is explore a package called Numpy. It'll make, I don't know if it'll make sense. It'll be apparent when we get there in a second. Some things we've been doing so far, we've essentially been doing it the hard way. And when we get to Numpy, we'll be doing stuff a less hard way. Let's see. This class. I don't think there's anything on the syllabus. Okay, I'm going to go back to 8 on purpose. So remember, thanks for letting me just talk away and not tell me there was nothing to look at. So remember a couple of meetings ago, we talked about vectors and matrices. Key things from that relevant to today's topic are how to define them and some matrix arithmetic. So I'll recall I got the cool picture downloaded from the matrix, so it's just like watching the movie, only better. And we built matrices in this fashion, where it was a list of lists. Each sublist inside the outer list was a row of a matrix. At least that's how we constructed it. And then we looked at some arithmetic, and the scripts themselves aren't all that hard for things like multiplication. But somewhere down here, when we get to dealing with either Gaussian reduction with pivoting or matrix inversion, the scripts get a little bit longer. They have a 1, 2, some cases triple subscripting component to perform the indicated arithmetic. So an alternative is to use a package called Numpy, which I think means Numerical Python, but it could be how my fingers feel after walking across from the parking lot. And when we employ this package, some of that matrix operations, they aren't changed. It's doing the same thing, but it's easier for us as operators of the machinery to create it. So our goal today is to get a little bit of exposure to Numpy, and we'll perform some mathematical operations using the Numpy package. All right, reading to you in case you can't read faster than I can talk, which is pretty unlikely. Most people can read way faster than I can talk. Numpy is a core library for scientific computing in Python. It provides high performance multidimensional array objects and tools for working with these arrays. The library's name is short for Numeric Python and Numerical Python. If you want to learn more, you can go here. And that in and of itself doesn't really learn you more, but this is a good tool to have. They call these cheat sheets, which I think is probably a bad naming thing because it implies that cheating's okay. A short reference sheet would be as good a name, if not better. So in the Numpy arrays, we have one-dimensional arrays, two-dimensional arrays, and actually more than 3, but 3-dimensional arrays. These are the most common data structures inside Numpy. The 0 axis corresponds to rows. The 1 axis corresponds to columns in the 2D. The 0 axis obviously corresponds to just the columns in a 1D. And then the, see if I can get this picture right. The 0 axis in an array, a 3D array, corresponds to a layer. The 1 axis corresponds to a row in that layer, and the 2 axis would correspond to a column in that layer. So you can think of 3Ds as 2-dimensional arrays stacked on top of one another. Other than a good mental model, there's no physical reason for that to be so, but that's how they are conceptualized by the builders of these. And then there's a whole series of things that we can do. We can create arrays, we can perform input and output through various methods. We can save them and retrieve them. We can look at the contents. We can ask for help. That's actually totally useless. And then array mathematics. So there is a link in the instructor notes on how to get to that cheat sheet. So the Numpy library has two fundamental conceptualizations. The first are data representations or data structures called arrays. So we've seen two of those three already, vectors and matrices. And I don't know what a three-dimensional array is called. Well, the matrix is a pixel. The three-dimension has to be a voxel, but I don't know what the name for a three-dimensional array is. Tensor, I guess that's a good name as any. And then it has data operations that are performed on the contents of those data structures. There's element by element arithmetic, which is actually quite simplified in Numpy. The arithmetic's not simple, but for us to invoke, it's pretty simple. And mathematical operations, there's matrix and vector arithmetic. There's indexing, selection, and copy. Lions and tigers and bears. I heard no my out there, thank you. The main computational thinking concepts expressed in Numpy are decomposition, so we can take things apart, abstraction, this idea of a three-dimensional array, there's no real physical manifestation of that. It's just an abstraction and an efficient way of looking at numbers for certain application. And then algorithms, which are the series of steps. So to set up the Numpy module, in your installs, you shouldn't have to do anything special. You should just be able to do import Numpy and have it work. You have to remember that you got to make that step in your scripts, otherwise it won't work. If it doesn't work for you, then you're in the world of installation or pain and suffering, whichever you care to fit. And so like we've done with all the other packages, pretty table, being the primary example, you had to go into the Amazon command prompt, type something like sudo install numpy and let it take care of things. Now this is the script that works on the machine that we're looking at right now. There's no guarantee that that will work on yours because there's no guarantee that your stuff is installed in opt, Jupyter Hub, bin, Python. The process is similar on Windows and Macintosh. Best is to hope it worked good in Anaconda and you don't have to mess with this. If you have to do the install, here's a few links that might be useful to you. So and then here's some links for useful videos of using the Conda package manager. Okay, I hope you don't have to, because this is that part of free software called the yo-yo component. Means you're on your own. All right, so moving on, numerical Python. We're going to start with an array. So this array has the same intellectual concept that Ray did back a few meetings ago when we introduced the array package, at least briefly. A one-dimensional array can be thought of as a vector. Call it Victor, so you can say what's your vector, Victor, and you can watch airplane movie over and over again. The position indices are as depicted there. They correspond to different cells in that vector, if you will. And for example, in that picture up there, right there, staring at the face, the contents of whatever 1D array is named at position 0 is a 10. The contents at position 1 is a 15, 2 is 7, and so on. And that axis would be called the 0 axis in a 1D array. And we actually don't have to specify axis in 1D. When we get to a two-dimensional array, there's a row axis, which is axis 0, and there's a column axis, which is axis 1. And it's very obvious what's happening. If you add dimensionality, the zero axis keeps moving forward. So the in a 3-array array, the zero axis would represent there, the one axis row, two axis column. But 2D array is probably the most of what we'll end up working with. So we have index positions 0, 1, and 2 for the 3 rows in this particular drawing, and index positions 0 through 3 for the 4 columns in the array. For example, the contents of 2D array at position 1, 2 is what? I agree. And the index accessing of the array is probably exactly as you've had in your head, if you're awake enough. It's a row, column, indexing, and each of them goes in their own square bracket. We'll see some examples of that shortly. To make a NumPy array, we can simply use np.array. Well, I actually got to change these notes because np I'm pretty sure is an alias. Yeah, it's an alias. So if this was to be written correctly, it would say numpy.array to create the array. And don't forget to work with the array function. You have to make sure that NumPy library is present. If you want to read more between a Python list and a NumPy array, go to the University of Central Florida and get completely uninterpretable examples. But it's there. So let's go look at some examples, but let's actually do them live instead of Memorex. Oh, it knows it's me. Some level I should be scared of that thing, doing it without asking for a password. We'll go to our friend Untitled 3. Yeah, we don't need that. Take my scissors. So there is my Untitled 3. And we'll go ahead and we will so what we're going to do here, we'll import the NumPy package. We're not going to do anything special. We're not going to rename it NP. And then we'll create a list, and we're just going to get the type of what my list is. So as of right now, we're not actually using NumPy. And it tells me that my list is a list. Duh. Let's print the contents of it. And we will get what we expect. So we expect it to start with a square bracket, return a 2000, then a 2001, and so forth. Sure enough, it does. There. Now we're going to modify things. We're going to take our list. We'll use NumPy, and we'll create an array from that list. And because we don't mind clobbering stuff, we're going to go ahead and put the result of that back into the object named myList. And then we will have it tell us what type my list is. So before I hit enter and make it and run this cell, currently the object named myList is what kind of object? It's a list. So now I'm going to go ahead and use the NumPy package. Now the object named myList is a NumPy array. It's changed data type. So the obvious question is, so what? If we print the contents, slightly different. What's the difference between the two? We'll go where's Waldo on here? Yeah, the commas seem to be missing. Let's see. Let's just pick the second element of my list and see if it's indexable. Sure enough, it is. And that probably would have worked before. So other than the commas missing, it doesn't appear that NumPy has done a whole lot for us. And if this was all NumPy did, I would agree with that assessment. It just made things harder. Now we'll make another list called my 2D list, because again, no creativity. And my 2D list is still just a list. If we print it, we get the list back. How many elements are in the outer list of my 2D list right now? 3. How many is in any one of the inner lists? 3. So it's a list of 3 things. Each thing has 3 things in it. So it's got a total of 9 elements right now, but that's not a very good visual representation. So we'll go ahead and convert it into a NumPy array. And typing the array on output is not necessary all the time. Okay, so now we've printed it. It still looks like a structure that has 3 things in it. In this case, there's 3 rows, and then each row has 3 things in it. So that's essentially unchanged. But what is changed is we just printed our matrix row-wise by row. Remember what it took to do that? If we were operating with it, it's just a list. I know that was like 5 days ago, but so if you remember 4 or 5 days ago, to print the matrix row-wise, we had to figure out how long the matrix was ourselves. Then we would use a for loop for row in range, the length of the object, and then we would print across each row to get the same thing. So here we have greatly reduced our human workload in constructing matrix output. Now, why we care might be somewhat irrelevant at this point, but it's a huge difference. So if we get the length of my list, if we ask for the length of it without qualifying it, without stating the axis, by default, it's going to use, I'm pretty sure it uses the 0 axis, and it tells us that there's 3 things in it. So if I do that, I should get, I'm asking it to do the same thing. If we specify the axis, oh, I bet you I may get a purple. Okay, it did work. Sometimes I get the pink box because I'm not thinking when I'm typing. So that's telling us how many rows there are. If we choose axis 1, which is the column axis, in this case, it's also going to be 3. We get the column axis. So now no longer do we have to go through and pick a row at, not at random, but pick the first element and then get one of the sub lists and then count how many things is in it. This is doing it for us. It's the same code we would have written, but it's embedded into the package. And we also can get the shape. A smart-ass programmer would have hacked into the GitHub site where this is all stored publicly and changed it and have it say square or rectangular. But instead, the non-smart ass ones just tell us that it's 3 by 3. 3 rows, 3 columns. All right, so that's a teensy introduction to creating things in NumPy. We also can go up in dimensionality. So we're going to have another list called my other list, and my other list is going to have an outer list, and it's going to comprise of 1, 2, 3, 4, 5 things. Well, we'll go ahead and print the contents back to ourselves to see what it looks like as a list. Then we will use the Numpy package to get its shape and to interpret it as an array. So there's my other list printed as a list. It's a 5 by 2. And when we print it out using the NumPy thing, it is indeed 5 rows by 2 columns. So there's some economy of coding that's conferred to us by using the NumPy package. But it does more than just that. It has some nice array arithmetic features. So for example, it's interactive cell. Okay. Remember scalar multiplication from a couple of meetings ago? Remember when we did it before, we would get a value for the scalar, then we would have to determine the number of rows in the matrix and then perform the arithmetic scalar times row column of a particular matrix element and then return all that back into the right place. In this case, once vector is a, okay, so this is actually old-fashioned element by element. So this is exactly what we did a week ago. So if we enter a scalar value of 2, it should go 0, 24, 48. So there we did it our old way. Now we'll repeat the same thing as NumPy. I don't think the importation is necessary, but it's not going to hurt anything. So now we create it as a NumPy array. We will print the contents. So it's a NumPy array, and now we'll just perform the scalar multiplication simply by multiplying the array by the scalar. None of that for loop stuff. Okay, so we get the same results. So what we had to do before was that. Ignoring the comment, that's 4 lines, and we had to keep track of indexing. And if we got something wrong in here somewhere, it would be hard to locate. Now, to perform the same task, we just need that line and that line. So again, an economy of coding. We never did this our old way, but if we want to square the contents of the array, it's almost trivial. So we take array 1, we raise it to the power 2, and internally it knows to take each element of that array, square it, put it back into the array. No assignment, nothing on our part. Let it happen. Similarly, maximum values, minimum values are easy enough to deal with. The key method name being max. There's also min. We also can find the position of the biggest value. So we have a max value of 96 in the original array. Let's find out where the 96 is located. It tells us it's in position 8. Let's find our original array. It's somewhere back here. It happens to be the last thing. And that's actually really handy. Because even though in this case the example was an ordered array, if it was disordered, it can still go through, find the biggest thing, tell us what its position value is. And that's a handy. If you didn't have that feature built in, how would you find the location of the biggest thing in an array? In words, you don't have to give me Python script. Y'all didn't have enough coffee this morning, it shows. You got this array, it's got 10 things in it. How do you find the biggest thing in it? Yeah, you're on the right track. Keep going.
For loop that compares each of the next values to the original value. So that's the higher value. That's the variable.
Right. So just for fun, because we have enough time to do that, let's figure out how to do that. Let's declare big equal to minus 9E9. That seems like a pretty small number. And then for I in range length I can't do a numpy Victor vector. That's what we'll do. I don't actually want to use an array. I want to use VICTOR. So what that's going to do is it's going to look, it gives us the ability to look through the contents of Victor vector one thing at a time. So if probably should do greater than or equal to big. If that's true, then we put that into big, else we just continue. So there's our logic structure. We have to do one thing, which is to keep track of the index. Start at 0. Every time we push the contents of something in Victor vector, we can index equals I. And at some point, want to report back to ourselves. And let's just do it the same way they do. They just report the actual index. So print. All right, assuming I haven't screwed something up, that is the script we would have to do the equivalent of print numpy argmax array1. Let's test that conjecture. So the 96 is the 8th thing in the array. So there's 2 things that work great, and I'm going to feel like I've earned a little bit of my money today. Otherwise, I'm going to get the dreaded. What else happens when it doesn't work? You get the dreaded pink box of encouragement. So a lot more economical to use the built-in stuff if you have access to the package. And that's not the hardest thing in the world to find the location of the biggest thing. But let's go ahead and give it a bit of a let's say you have 2 biggest things. Which one did I turn? 48. Okay, so we've got our deal back. If we do the same thing, that's what I was after. Okay, so now we have an array that has 2 biggest things in it. They're identical value. Let's see what NumPy does. It finds the first one. Let's see what our homebrew does. It finds the second one. That was because of the less than or equal requirement. So NumPy by design finds the lowest valued index, the lowest numbered index of the biggest thing. And I'm sure there's switches that you can put in the argmax function to have it find all the big values. And here we would have to, for our homebrew one, our logic to be able to find all the big values would be a little bit more elaborate. Because we would still want to perform this test, probably index would make more sense in this case as an empty object. And we would append to it things that we're counting and print it. And so now let's see if it can find. Didn't want that to happen. Index append. I'm just going to leave it be. We're close, but we'd have to do something like that to be able to get all the indices. And I'm more than positive that the NumPy argmax has the ability to do that for you. Similarly, we could find the minimum value the same way using the argmin or the min function. We're going to define another array called array2. Let me get this back to being correct. I'd rather have it working right and be correct than working wrong and be incorrect. So here's array number 2. And if we want to add the two arrays together, and I just leave them as B, we simply can add the two arrays or take a difference. So remember adding two arrays in lab, I guess it was 8, lab 8. For any of you that have looked at it, we'll just do next Wednesday, this Wednesday. So again, you had the for loop, you had to check sizes, and then you had to count through, do array 3 equals array 1, position 1, position ij, plus array 2, position ij, and put that into array 3. Here we just type the two array names, put a plus sign between them, and let the package handle it. In fact, we don't even have to tell it that it's a NumPy package because the type of these two data structures is already a NumPy array. It just knows. And so there's the two arrays added together. And I think putting that second 96 in my case kind of messes things up, but it doesn't damage anything. And try to do that. And the other one is element by element multiplication is simply name the two arrays, put a multiply sign between them, and let it rip. And so let's think what the two arrays are. We have one array that has a -12, another one has a 0. So that first element after multiplication should be 0. See, the second one is 0, and then whatever number is. So we should get 2 zeros, and then I think we'll start getting numbers out of it. I guess 0 is a number. So we do that. There's those first 2 zeros, and then the multiplication. Something I've never tried. See what division does. You probably should get the pink box of encouragement. Why? Before I hit it, tell me why. Well, you can. It just doesn't know what to do. So it goes pink. And it says runtime warning, divide by 0 encountered. So unless we override that and tell the machine how to divide by 0, we get a response like that. And that's likely to happen from time to time. So let's see what we could do. Well, I am curious to see what would happen if, where's array 1? If that had a non-zero value. And where's my other array? My array 2. All right, so now the two arrays are entirely non-zero. Let's see if element by element division works. Sure enough, it does. That's actually really pretty cool. Why you might need to use that, I have no clue, but it's nice to know it can do that. And we can also do more conventional array arithmetic. So we've done those already. Oh, with multidimensional arrays. So we'll just go take a look. We won't look at those. I'm going to use that. I might use that later. So let me go ahead and create our new arrays. So now we're going into two-dimensional arrays. So array 1 is the square matrix 5, 10, 15, 20. Oh, that's cool. And array 2 is a different matrix, also 2 by 2, 6, 9. And most of those operations are defined regardless of the dimensionality of the array. Element by element, as long as they are the same size, is defined in NumPy. And it's a property of the NumPy array. We don't have to tell anything special when we add things together. So here we're going to add the two arrays and then difference them. So the first one, the upper left-hand corner will be 8, and then when we difference them, it should be a 2, and so on, as expected. And we have other games we can play. First, we have a couple of different types of multiplication. Let me go ahead and load this and run it because it looks like I left one off the list. I'll explain what they are in a second. I think this is defined. So this first one, array 1 times array 2, I'm attempting to do element by element multiplication. So my 3 times 5, I should get 15. 10 times 6, I should get a 60, and so on. The second one is called the matrix product. And the third one is a dot product, which we studied before. And let's see what happens. Okay, so the first one, 5 times 3 is 15 as expected. What was the other two? 10 times 6 is 60. So there's the first matrix that made sense to us. Our second one, which is array 1 dot array 2, what that did is it took the first row of array 1, multiplied it by the first column of array 2 as a dot product, and put that result in the upper left-hand corner. Then it did the first row of array 1, multiplied by the second column of array 2 as a dot product, and put that in the upper right-hand corner. And accordingly for dot product. It looks like this outer product sign, at least on a 2 by 2, produces identical solution to the inner product, which I guess actually that kind of makes sense. When we get to higher dimensions, this product and this product will produce different results because they're actually operating. So the outer product you'll get in your mechanics classes is a mixed triple product or a cross product. 2 by 2, it doesn't make a lot of sense. Now, if we had to do it with ordinary lists, just the inner product. So I'll paste that. We're simply going to do the equivalent of those 3 lines of code. If we did it the way we did back in lesson number 8, there is pretty much a minimal script that would be required. To define the 2 matrices, you always have to do that. There's nothing special there. We have to have a destination matrix. We're implicitly assuming the sizes are correct. We'll create that matrix full of zeros called the C matrix. Then element by element to get the row and column multiplication correct. We have a triple subscripted loop or triple nested loop. And then finally, we will print the results back out row-wise. And yes, we got the same results, but if you consider everything you type as a chance to make an error, it's going to cause you to have to go get a job at Subway or Bennigan's. The less you have to type to accomplish a task, the better. The fewer chances you have to make an error. All right, so at this point, all I've really demonstrated is that NumPy is a simpler way to do matrix arithmetic. And if that's all you get out of it, that's awesome. That's a good thing for the day. Again, we can find the position of maximum or minimum values in a multidimensional array, and it's going to return not what I expected. One, two. Not sure that's actually correct. I'll go look that up later. We also have some measurements available to us. We have the ability to get mean values. So if the array is angry and mean, we can get the average of every component of the array. So the first line there is going to take the array, which is the 105, 115, 225, 330, and compute the mean of those four. So mean is like the average. So who can tell by looking at it what the mean should come close to? So you got 105 and 150 is like about a 125, 225 and 330 is could be 270 something. So somewhere between the two, about 250. So somewhere between 225 and 300 looks about right. Let's see what we get. 202. We're not bad. And then the mean value of axis 0, which is along the rows, is taking the mean of those two and those two, and then computing the mean of that. So that's a lot easier than doing it element by element. Some of the other functions in NumPy that we have associated with us is something called arange, which will return an evenly spaced set of array elements. We define the range. Linear spacing, evenly spaced array elements. Zeros produces an array of zeros in it. Ones produces an array of ones in it. They don't have twos, I don't think. Random.rand_int returns random integers. That's occasionally useful, and we'll use it to help add to your current confusion. And then there's some functions that perform operations on NumPy's arrays. So min and max we've already seen. Argmin and argmax, we've already seen examples of that. I'm not sure if we did sum. We have not done reshape yet. We have not done sort. But sorting is a very powerful feature that's built in. So if you were having this class 15 to 20 years ago, after we did repetitive calculations, we would have spent about a week discussing different sorting algorithms. And we would do like a bubble sort, which is computationally terribly inefficient, but it's really easy to explain. Shell sort, straight insertion sort, heap sort. Ultimately, we'd arrive at an algorithm called quick sort. I don't have to do that anymore. We have the keyword sort, and it does it for us. And it either uses straight insertion if the array has got about less than 50 things in it, or it goes straight to a quick sort algorithm. So that's a nice improvement over the olden days. You might ask yourself why sorting might even be important. Anyone here use Google last day or two? Search for something? So it didn't actually do a search. Those searches are done when the load on the network is really low, and they save them as sorts. So when you did a search, you actually found the most recent sort that had the keywords that you put in. And that's why it can produce 150,000 things in a fraction of a second. It's pretty cool. Some functions that we have available to us are square root, exponent, sine, cosine, log. And given that you all are packing up, getting ready to leave, and I just looked at the clock, I guess it's time for me to shut up. Lab's gonna be fun for you all today because we didn't get far enough. That's okay. You have the lesson. You can refer to that as you're going to lab. So I'll see you in a little bit in the lab time. Have a great week.